Hello, everyone. So I'm a new organizer of this webinar, and Taiki is the first speaker I invite to this webinar. So Taiki Yamada is at the University of Tokyo, and who will talk about unconstrained realization for dynamical systems. So please start, Taiki.
Okay, so thank you for your introduction. So good afternoon. So again, I'd like to say thank you very much for giving me this opportunity to speak at the NCTS online seminar. And first of all, I'd like to thank the organizers, including Tokta-san, for inviting me and for arranging this seminar. So today, I will talk about constrained realization for dynamical systems. So I should first clarify that the constraint realization is not yet fully established mathematical theory. Rather, I introduce it today as a tentative viewpoint to facilitate discussion today. So my aim is not to present a complete theory, but to share this viewpoint and discuss whether it can help us organize several problems that have studied in the context of neuroscience. So let me first explain my position in science. So my research is located around neurocomputing and computational neuroscience and mathematical neuroscience. The neurocomputing develops a brain-inspired system just for application usage. And computational neuroscience try to analyze the brain models in order to understand and predict the behavior of actual brain. So these two directions are closely related, but their motivation are slightly different. So recently, I have become increasingly interested in mathematical neuroscience. Mathematical neuroscience is not only about analyzing specific brain models or systems, and trying to establish mathematical theory behind them. But if I may say this bravely, I think mathematical neuroscience is still a young field. So it is promising, but we do not yet enough common concept to organize different models and systems in the neuroscience. So for this reason, I am very happy to share the tentative viewpoint constraint realization in an opportunity like this NCTS, a seminar where mathematical discussion is strongly encouraged. So the outline is as follows. This talk has two parallel goals. The first goal is to introduce the constraint realization problem as a tentative viewpoint. Again, this is not yet complete. It is not yet completed mathematical theory, so I highly encourage you to discuss on it in order to refine it for future. So I introduce it today mainly to facilitate the discussion. The second goal is to present two case studies from my previous work. The first one is about dynamical system learning, and the second one is about learning rule realization, and both are from the context of neuroscience. These two goals are parallel, so I will introduce the abstract viewpoint through concrete those two examples. And at the same time, I will use the example to test whether the viewpoint is useful for further discussion. And through those examples, I will refer my previous work. So you may also see some machine learning topics. But the machine learning topics are just an example. The main theme is constraint realization. So I'd like to dive into the content. The first, I'd like to introduce the notion of the constraint realization problem. The constraint realization problem is motivated by the problem about realistic learning and approximation of the mathematical object. The definition is here. So we first consider U as a universal set, and the constraint realization problem is defined as a triple F, C, and R, and F is the element of U, and C is a subset of U, and R is the equivalent relation on the universal set U. And we say the problem FCR is solvable if there exists element G in C such that G is equivalent to F in the sense of equivalence relation R. So this constraint realization problem is motivated by the approximation of the dynamical system in the dynamical system with assumption of structural stability. You may be familiar with it. So the structural stability of dynamical system F is defined by the following. So we say the F is structurally stable if there is epsilon such that for all G in the epsilon neighbor of F in a specific distance function D, F and G are regarded as equivalent as a dynamical system, topologically conjugate. And this structural stability is kind of their notion to the bifurcation of the dynamical system. So let us consider that we want to approximate the system F, which exhibit the behavior like this. And we'd like to reach to this F by realistic realization C. And in realistic situation, in generally, the set C is the strict subset of U. In other words, in realistic situation, it is impossible to reach all of elements in U by constraint realization. Right. And we'd like to consider situation where even in such constraint, owing to the equivalence relation R, we can guarantee the equivalence between the realized object G and the actual target F. And this situation is formalized as the constraint realization problem like this. So in order to get familiar with the notion of constraint realization problem, as it is tentative notion I just introduced. So we'd like to see the trivial case regarding the solvability of the constraint realization. So the first trivial case is that the target object F is in the target system F is in the set of C. Then the problem is obviously solvable for any R because we just take F from the set C. And on the other hand, if the target object F is not in the set C, then it implies that the diagonal equivalence relation there cannot be guaranteed solvable problem since diagonal equivalence relation requires exact matching between G and F as exact matching between G and F as the element of the set. So in other words, in the case F is not the element C, it requires non-trivial equivalence relation R. In addition to the above case, I'd like to emphasize the kind of monotonicity of the constraint realization problem. So we first suppose that the triple FCR is solvable. And as I introduce C and R as a subset of some set, so the inclusion relation between subset yielding the natural order for them. And for example, if the C prime is larger than C, and it is obvious that the triple F and C prime and R is also solvable due to solvability of the original problem. It is we can have the similar statement for equivalence relation R. So those observation implying that the smaller C and R, which guarantee the solvability of the problem, are non-trivial, and the point that the point which we'd like to discuss. So those observations implying the fundamental questions regarding constraint realization problem in this study. So the first one is when we suppose the triple is solvable, then we'd like to ask the C and R is minimal or not. And the second point is if the second point is the target object F is not the element of C, then we require non-trivial R. So we'd like to ask that when the triple is solvable. So I'd like to share our previous work in the context of those two fundamental questions on the constraint realization problem. So I'd like to dive into the case study for the problem 1. Okay. So in this case study 1, so I'd like to consider dynamical system learning. Again, so please keep in please keep you in mind that this fundamental question is the main core of the talk, and just I'd like to share just an example based on my work. For the dynamical system learning, the background is following. So in the previous work, the computational algorithm for topological dynamical system learning was proposed. And in the context of this talk, the previous study can be regarded as showing the proof for the solvability in the case of the equivalence relation R as a topological conjugacy. So I will introduce the definition of it later. And for that background, our study can be positioned as a reformulation of the existing algorithm by considering brain constraint, and it yielding the constraint subset of C to realize dynamical system. And in that sense, our study can be positioned as a refinement of the C by introducing smaller C, which guarantee the solvable triple, defining constraint realization problem.
Taiki, can I ask a question? Hi.
Sure.
Hello.
Sure.
Yes. So you have a background and you have our study. So you have a F and C and R. And in our study, what is F, what is C, and what is R?
Yeah. Thank you for questions. So in this talk, I'd like to set the universal set U as a set of dynamical systems. So so F is F is one target dynamical system, and the C is a set of dynamical systems.
Yes.
System which can be constructible under the constraint.
So the constraint can be realized by experiments or not. It's a something given or something you have to do experiment to obtain or do numerics or I don't. So my question is, of course, it's a set or subset. I know this, but I want to understand in your study, for example, about the constraint of a brand. How can you identify or realize F, C, and R? Maybe R is given, I know, but how about C and F and?
Yeah, so I think it is interesting point. So as you mentioned, there is a variety of the way to define the C in the context of brain, in the context of neuroscience, and I'd like to fix as an example of C in this talk, and I will explain the detail of C in each example later. So
okay. Thank you. Okay.
Just thank you for question. Please feel free to interrupt me during the presentation. So I'd like to consider the dynamical system learning for the first case. So first, I'd like to define the problem at topological dynamical system learning. So in order to do so, I will define the topological dynamical system and the topological conjugacy as an equivalence relation between two dynamical systems. And so in this study, I will consider a discrete time dynamical system, autonomous dynamical system, and we call this capital X denotes the state space, and F determines the map for the evolution of the state in the state space. And we call the pair XF as a topological dynamical system. And we'd like to introduce the equivalence relation between dynamical systems, namely topological conjugacy. So we say that two dynamical systems, XF and YG, are topologically conjugate if there is a homeomorphism H, and satisfying this conjugate relation. So by considering topological conjugacy, the qualitative behavior of F and G are preserved. So we like to use this relation as an equivalence between dynamical systems. And the purpose of topological dynamical system learning is for given true unknown dynamical system F and the data D from it. We like to creating the G, which is topologically conjugate with the original dynamical system F. So in the previous work, in the previous work, the algorithm to achieve topological dynamical system learning was proposed. So I'd like to introduce its algorithm.
Taiki, sorry, I have a question. Can you go
Sure.
back to the previous slide?
Yeah.
Yes. Yes. If this approach is possible, then I think you need to a priori beforehand know that F is charge stable. Is this true? I mean, do you need to know anything about the F? Because if F is not charge stable, then maybe there's no such G.
Yeah,
Right?
exactly.
So do you assume that F is already charge stable?
So I understand your question partially. So yeah.
Okay, so of course, being charge stable is almost generic. Yeah, there are counter example I know, but do you? Okay, my question is, do you assume anything on F?
Yeah. So so in that sense, in that sense, so the answer for it is, the answer for the question is it is not established as a theory. So in other words, in this talk, I cannot specify the exact assumption on the F which guarantees solvability. So, however, as you mentioned, in order to in order to in order to realization candidate G exist, we require some assumption on F, for example, stationarity or
Yes.
yeah.
Okay, but okay, I see. That's this issue. Thank you.
Thank you so much. So I'd like to introduce the algorithm, which is introduced in previous work. So here's a problem setting. We first assume that there is fixed a target dynamical system XF, and we consider the following model to generate the data. So we already have the target dynamical system, which defined the evolution as the state xt to xt plus 1. And we assume that the extra variable y is obtained by this dynamics. This dynamics depending on the true state xt, where the sigma is a nonlinear activation function, and A and B are metrics, A and B are fixed metrics. So in this model, by fixing target dynamical system XF and property of the model sigma and A and B, then we can obtain the sequence of YT. And the algorithm to achieve the topological dynamical system learning is as follows. So in this algorithm, it assumes that data D is the pair of xt and yt with the time correspondence. And in order, and the output of this algorithm is learned dynamical system G. And G is defined by this equation, and this equation where W is learned by the W is a matrix learned by given data D like this. So intuitively saying that this W is learned so that this W is learned so that WYT approximate XT and resulting in the learned dynamical system G approximates the behavior of YT, which is driven by true dynamical system. Okay. So here is a recap of this algorithm, and it can be shown that this algorithm guarantee the guarantee of success of topological dynamical system learning under the topological dynamical system learning under several assumptions. So the first assumption is that regarding the target dynamical system F, and first we assume that the dynamical system F has attractor A, and also we assume that regarding the synchronization between the target dynamical system and the variable y by specifying by the mapping phi. And this mapping phi is satisfying this equation, representing temporal synchronization between xt and yt. And finally, we assume that for round matrix W is sufficiently accurate due to the sufficiently large number of data set, the number of data, capital T. And by those assumptions, we can prove that round dynamical system restricted on the specific subspace of state space is topologically conjugate to the original dynamical system on the attractor A. So its proof is very straightforward. So as topologically, in order to prove the topologically conjugacy between dynamical system, so we need to prove the conjugate relation between F and G. So we'd like to start.
Yeah.
Sure.
So yes, thank you. So Taiki, now understand here you need your F to be how to say, you restrict your F to the attractor. And if I remember correctly, attractor is kind of stable, and because of invariance, you can have a conjugacy. But now my question is, in reality, F is unknown. A is also an unknown, right?
Yeah.
So a priori, you don't need So now, in your learning, you have to know F and A both object, not just F. Is this correct? Do you also need to know A? Because if the original setting is a X, right? X is a phase space or something like that, or the set of the phase space. The phase space is given, that's fine. But attractor is something one should learn also. Is this right?
Yeah.
Please.
I think you are right. So basically, in order to learn the property of dynamical system, we need to get some data regarding the dynamical system. And as you mentioned, in order to know the attractor A, in this problem setting, they require to use the sequence of xt which belong to the attractor on it. So in that sense, that the information about attractor is partially informed through the sequence of xt in this problem setting. However, I'm going to introduce our work to remove the assumption of availability xt. So that's why you have a point.
Oh, okay. Thank you.
So here I'd like to briefly explain the equation. So this proves the topological conjugacy between F and G. So first, the first equation is from the definition of F and phi. So more specifically, fxt is xt plus 1 by definition, and phi maps to y with the same phi maps x to y with the same time point. So this is equivalent to yt plus 1 owing to this assumption. The second equation, the second equal is due to the assumption from is due to the third assumption. So we assume that round dynamical system G can can approximate the approximate behavior of yt to yt plus 1 with sufficient accuracy. And again, so we'd like to use the assumption regarding the synchronization phi. So the yt can be mapped to so the yt that can be written by phi xt by the mapping due to phi. So this equation, this equation proves that topological conjugacy between F and G on its orbit and on its orbit xt, and the minimality of the attractor A, implying that this equation holds for all x in A. Okay.
I have a question.
Sure.
So some of the equalities are probably like error estimates. So are these like inequalities instead of like a usual topological conjugacy? For example, yt plus 1 equals g of yt. You said like sufficiently large t, this is equal, like approximately. So this doesn't seem to be an equality, but it's like a, I don't know, like an error estimate.
Yeah.
Yeah, exactly. So the first I'd like to say that so far there is no there is no treatment to guarantee the finite to guarantee the topological conjugacy in the finite number of data t, and so basically it is. So actually, you have a point, and basically it is hard to get the exact equality for this example if we consider error, and also the focus of my talk is not about the validity of algorithm, but is not about validity of algorithm, but refinement of it. So I'd like to explain its idea briefly for this time. However, I admit that especially for this term, it requires some error. It requires error treatment for future.
Okay, thank you.
So can I say something? I want to give some remark to Yuya's question. Yes, yeah, I think this theorem in reality is like approximation theory, not just everything is so perfect equal. And to me, it looks like a shadowing lemma, something like the true orbit and pseudo orbit. There's a error which you can control by such a theorem. Okay, this is my interpretation of the theorem. And now I somehow think of how you control or how to say, identify the global attractor. That's a so-called Tarkin's embedding theorem. Maybe in your data, you can also use the delay coordinates to approximate the global attractor first. So you have an approximate attractor, and then you do your forward time sequence series. So I mean, somehow, I want to answer my question. The identification of a global attractor is an assumption, but if that's true, there exists a global attractor, then that should not cause any problem anymore. So I can go back to your problem setting. Okay, this is my remark. And everything should be, as you are saying, should be like the error estimate, error control. Yeah, very good. Thank you.
Yeah.
Nice.
Yeah, so I appreciate you I appreciate you for pointing us the relation to the Tarkin's embedding theorem. So actually, the model I used to generate the sequence of YT. The YT can be regarded as a generalization of delay embedding for specific choice sigma and A and B. So yeah, so we can see.
I don't see any delay. Can I see any delay here? Where is the delay? I am interested in this. Where is the delay?
So, for example, in order to recover the delay embedding from this equation, we set sigma is identity function, and A as how can I say A as a matrix with as a matrix with A as a matrix with zero element. The zero element otherwise first column to insert the information X the point wisely, and the matrix B will introduce a delay which relate to delay embedding at time point t and time point t plus 1. So yeah, so this can be regarded as a generalization of the embedding to get the observation, and this algorithm try to construct the dynamical system on the embedding space, and that's why it can recover that can recover the original topological dynamical system.
Cool. Thank you. Thank you.
Sure. So I introduced the previous work, so I'd like to go into our contribution. So our observation on the existing algorithm here is that the availability of true state X is problematic, as we mentioned earlier. So such motivation comes from the neuroscience context. So in this problem formulation, we can interpret the target dynamical system as a dynamics outside as a dynamics of outside world, and those observation YT and processing can be regarded as information processing inside the brain. So in that sense, from the view of mathematical neuroscience, it is kind of unnatural to have XT here, since it is information processing inside the brain. And also, and also in the previous work, I assume that the sequence of XT is available, and in that case, the original mapping F, which map XT to XT plus 1 itself can be approximated by using D, and this corresponds to the case where the target object F is the target object F is element of C here, and as we observed at the first place. At the first place, such situation such situation prohibit the non-trivial R, so it makes the constraint realization problem it makes constraint realization problem trivial. So our motivation is that we'd like to remove the assumption of the availability of xt here. And we show that it is actually possible by simple reformulation of the algorithm. So in our formulation, we only assume that the sequence of yt is available as a data. And in order to create the round dynamical system G, in our formulation, we will learn the matrix theta and the matrix theta in the definition of round dynamical system, and this theta this theta is defined as a minimizer of this function defined by the given data. The given data d prime again, which is only which depends only on y here. I'd like to emphasize that our algorithm is valid as the previous algorithm. So the intuitive explanation for the validity of the algorithm I explained earlier is also applied for our algorithm, since those yields identical result for identical result in topological dynamical system learning. So I introduce our work to reformulate the algorithm for topological dynamical system learning. So again, in previous formulation, it require a pair of xt and yt as a data, and it construct the round dynamical system G like this. And the beauty of the previous work is that it has the explanation for its validity by using topological conjugacy. So it has connection to the constraint realization problem we'd like to discuss here. So and compared with previous work, our work can be regarded as a reformulation of a previous work by reducing the assumption on the available data here. And our formulation depends only on yt and yielding identical result on the topological dynamical system learning. So and for the learning of the matrix theta in our formulation, the formulation has similar structure with existing unsupervised learning method called dynamic mode decomposition. And in dynamic mode decomposition, similar to our formulation, it requires only the sequence of yt, and it calculates the matrix K satisfying this approximation, so we can see the correspondence between K and theta. And in that sense, our formulation can be regarded as a generalization of the dynamic mode decomposition. So it should be remarked that for dynamic model decomposition, although it can reconstruct some features of original dynamical system F, still being struggle with it can being struggle with the struggle with making relation to the topologically to the relation to topological dynamical system theory. So in other words, dynamic mode decomposition has similar structure with our formulation. But, however, it cannot relate to the equivalence relation topologically conjugacy. So in that sense, our formulation provides tentatively the minimal C in the constraint realization problem in the context of topological dynamical system learning. Okay. So so here I explained the first case. The first case as an example of dynamical system learning. So I'd like to go into the next example. Example based on our work, and again I'd like to emphasize that the core of the talk is about constraint realization problem, and fundamental question of it related to the second topic is that the second topic is the solvability of F and C and R. In the case the target object F is not the element of the possible C. Okay, so here is the background and our background and summary of our contribution for the case 2. So in the case 2, so we'd like to consider the learning dynamics in the brain. In the brain, and as a background, the learning dynamics in the brain has a constraint, namely its locality of the available information to process learning. So to process learning, this constraint yielding the brain-inspired C, namely the three. It is named as three-factor learning. I will introduce later. It is kind of model of the brain learning which satisfying this locality condition. And in order to consider learning dynamics, so the learning dynamics itself can be regarded also as a dynamical system, and its dynamics and its behavior and its behavior is categorized as a validity of learning validity of learning dynamics, but not specific matching. So in that sense, for the learning dynamics, the average behavior of them matters. This observation, introducing the equivalence relation between learning dynamics, namely stochastic equivalence, as a course view. So in our study, we like to investigate the condition on the target object F. Target object F that makes the problem solvable. Under the C and R introduced above. Okay. So I'd like to introduce the problem setting regarding brain learning model. So in this setting, so we would like to regard the brain model as a system with trainable parameter like this. So we assume that the brain model has the input X and output Y, and by adjusting the parameter W, we'd like to make input and output a desired to desired property. So in order to do so, I will introduce the following setting. So here small l, small l, which is a function of the parameter and the input and output. This function L quantifies the error of current parameter W for a given the pair of for a given input and output pair. So we'd like to basically like to minimize this function L. So in other words, the purpose of brain learning is to minimize the cost function, denoted by capital LW, defined by this equation. The very naive approach to achieve this is considering gradient descent on this cost function capital L. And so this gradient descent algorithm can be regarded as optimal dynamics F, optimal dynamics F. And this F is going to be considered as a target in the constraint realization problem. And as a brain learning model, so we use the three-factor learning model in this talk. The three-factor learning is a class of learning dynamics to update the parameter W, and it requires specific form of the updating rule for the parameter Wij. Namely, it should be multiplication of the corresponding input and output and the global scalar factor E. And E here the motivation of three-factor learning is implementing or formalize the locality of the brain learning in realistic case, namely inside the brain, in order to update the parameter Wij. The parameter Ij, the information which can be used for its updating is limited locally. So that's why the three-factor learning has this form of equation. The three-factor learning model yielding constraint dynamics by the constraint dynamics C with the function E as its parameter. So obviously, in general, the optimal gradient descent and three-factor learning rule. The three-factor learning rule are not much So we have to introduce cost view by considering equivalence relation R. So in this slide, I'd like to introduce the background regarding equivalence relation to make the problem solvable. So as a background, the stochastic gradient descent algorithm, which is defined by the following equation that can be regarded as equivalent learning algorithm by the equivalent learning algorithm under the equivalence relation for considering average behavior to the gradient descent. Well, this relation is come from the definition. It's come from the definition of the cost function capital L. So in this sense, stochastic gradient descent can be regarded as a sample-wise optimal learning algorithm, which approximate gradient descent in this sense. Well, by motivating this example, so we'd like to use a stochastic equivalence as an equivalence relation to consider the solvability of the problem with this F and C and R. Here, so we'd like to here this formulation motivates us to consider when this triple is solvable. In other words, in this example, we have to consider what condition on F for the specific global factor E to exist. So in our work, we worked on this problem. So here is a fundamental question regarding the original constraint problem, and in our setting, F is optimal gradient descent dynamics, and R is the stochastic equivalence relation, and the C is from the three-factor learning. In this setting, so we'd like to investigate the condition on F. We'd like to investigate a condition on F for C, for E to exist. And in our work, so we propose the analogy. We propose a view regarding the analogy to orthonormal basis expansion on this setting. So here, the orthonormal basis expansion on vector V allow us to express it as this form. So we can see the analogy between them. So like this, and basically we formalize this analogy by using the notion of a frame, which is a generalization of the basis, and we consider the solvability of the problem in the sense of the possibility of a frame expansion. And by analogy to the orthonormal basis expansion, the possibility of expansion can be checked whether target vector V is in the span of the basis Vi. So in our work, although I'm not go detail about the formulation, but so I'd like to emphasize the analogy. So in our work, basically we first prove that the term here, yx transpose is regarded as a frame, a generalizational basis for the subspace B defined by for subspace B defined by this equation, namely this subspace is a set of metrics with the set of metrics which is constructed by multiplication between W and symmetric matrix A. And owing to this lemma, we can have the theorem here by immediate consequence. So here the problem, the constraint realization problem FCR with above C and R is solvable if the optimal dynamic, or if the optimal learning dynamics F is in this subspace B. I'd like to summarize. I'd like to summarize our work on the second example in the context of the constraint realization problem. So basically, our theorem tells that if the target object F is in specific subset V, then the frame expansion is possible. So and it implies that there exists a function E satisfying this satisfying this stochastic equivalence between target and the three-factor learning. So the schematic overview is like this. So we specify the set of target object F V which allowing solvability of the problem. Here we can consider the possible theoretical extensions regarding case study 2. So for example, the smaller c can be one topic to be investigated. For example, although in our work we can show the existence of the global scalar factor E to satisfy this condition. But however, in the context of neuroscience, we need to consider that E should be implemented within the brain. So in other words, the function E should be sufficiently simple so that it can be implemented within the brain. So such consideration motivates us to consider smaller c and the solvability of the constraint realization problem. And also, while we consider the stochastic equivalence as R for the problem, maybe we can consider causal equivalence relation by accepting transformation on dynamical system as we consider in the first example, electropolishkary conjugacy. So it will make the variation of the constraint realization problem regarding brain learning theory. Additionally, I'd like to mention about the utility of the theory. So basically owing to the three-factor learning model, which is a brain-inspired learning model, it might contribute to energy. It might contribute to developing for the energy-efficient artificial intelligence. Since by considering the brain-inspired constraint, C, by considering it, we can develop the algorithm. We can develop the algorithm which requires less shared memory capacity and memory transmission, and it will potentially result in the energy efficient computation. Okay, so I'd like to conclude my talk by emphasizing underlying core concept constraint realization problem. So in this talk, first I introduce the notion of the constraint realization problem and its solvability. And in the case study 1, we consider the minimality of the constraint C by using the example in the topological dynamical system learning. And in the case 2, we investigated the condition of the target F, which makes the problem solvable. Under the case where C is where constraint C is come from macroscopic constraint on brain, and R is corresponds to the stochastic equivalence relation. So in this talk, I'd like to emphasize the idea of the constraint realization problem as a framework to investigate the limit or potential of the brain information processing. So here the framework allows us to consider the dynamics with brain constraint can realize the specific true or optimal dynamics F under the equivalence relation R. So in other words, by this framework, once we translate biological or realistic constraint on the brain into C, then we can consider the possible. Then we can consider possible or required mathematical features on the F and R, but by considering solvability of the constraint realization problem. So, in order to develop this notion in the mathematical neuroscience, several points here need to be investigated more. So, first of all, through those examples, the minimality of C or R in solvable problem is the matter. However, we don't have the strict theory to prove the minimality of C and R, but a theoretical guarantee. The theoretical guarantee for the minimality of C and R will contribute to understand possible realization within the brain more deeply. And also, again, through those examples, we can see that we can see that for solvable problem FCR, those F, C, and R relate to each other somehow. So I am interested in to investigate those relation between those relation between the member of this problem FCR to understand general situation regarding regarding constraint realization problem. And also, I'd like to remark that. I'd like to remark here that although I use a dynamical system, I use dynamical system as an example, or as an example of example for the case study the case study. However, the universal set U does not need to be a set of dynamical systems. So we can consider other situations where brain try to try to realize the other object other than dynamical systems. Finally, the equivalence relation R induces an order structure on the universal set U. So basically the current constraint realization problem consider the compatibility of this order structure and introduce C from the context of neuroscience. So it is natural to consider the compatibility with other structures on U, for example, algebraic structure or topological structure or feature. Okay, so I'd like to finish my talk. So I appreciate you for a great attention on the talk. Thank you.
Thank you, Taiki. So thank you for a wonderful talk and questions.
Yes, Taiki, thank you. I have a question. Oh, I have several questions, but let me ask one. Okay, first I want to check my understanding. As a mathematician, I saw people always start from F, okay? F, given. And then we want to prove the structure stability or topological conjugacy of F. Then it's very difficult, and we prove that, so there's a neighborhood, okay? Neighborhood such that you have this conjugacy classes in this neighborhood. But now I think you are doing the inverse problem, right? Because you don't know the unknown F. Now you have data, you want to construct G such that it approximates F sufficiently. And this is something I haven't thought of. But now I still think there should be some assumption on your dynamic system F or on the set U such that this works. But maybe you don't need this because you only have data, right? You cannot assume anything. So I really want to understand if somehow your algorithm, your theorem works. Is there any risk that in the end, there's no new discovery, new finding, there's no F. You understand my point? So
yeah,
it's possible that you can do everything you want, but in the end, there's no F. How can I avoid such risk?
First of all, I admit the existence of such risk if we consider specific C and R.
Yes.
And however, first of all, I'd like to insist that we do not have to avoid that situation in general. For example, actually, my motivation, my motivation my motivation as you my motivation as you understand is is that considering the inverse problem for given C and R from the motivation of the specific field. So we'd like to investigate whether the problem is actually solvable or not. In other words, the such F is exists or not. So
yes.
So in that sense, the absence of such F is not risk, but the statement that those C and R is too strict or it does not make any useful prediction at all, something like that.
So maybe this is like a statistical result. Can I interpret in this way? Can I put this in this way? It's like if you can approximate, if your data, your algorithm can give some pseudo prediction, then I have a high confidence there should exist some F. Can I put your result in this way? I mean, yes. I mean, if you somehow assume your dynamic system is dissipative, right? For example, the underlying dynamic system has some property, then of course there exists F. Then your method works. There's no risk. And if there's no such assumption on F, then as you say, if we don't need to avoid it, then what kind of conclusion we can draw from your study? This is yeah. Sorry, I still don't get it very well, but maybe this is my problem because this is completely new to me. Okay, so I am trying to.
Jayan. So
Yes.
in my understanding, he
Yes.
has data D, which
Yes.
is implicit. So which implicitly assume that some F exists.
No, but the F may not be structurally stable.
Yeah, I know. So, but yeah, there may be some weird F, but I think in his settings, it's more important the existence of data, not the
Yes.
statistically structurally stable function F.
Yeah, I believe in his data, but I don't know whether I should believe in his prediction. You know, this is something I am now trying to understand.
And related to Giant's question, I was maybe I got it wrong, but at the end of the topic circle 1, so Taiki, you discarded the first half x and y, and you discarded x.
Yes.
And now
Yeah,
I'm worried about the connection to the true dynamics. So I believe, I mean, I'm convinced that you can predict or approximate the data sufficiently well, but I'm not sure what you're approximating now.
The same question. Yeah.
Yeah. So the information about the true target system, for example, X and F, is implemented on Y. So our statement is that the information to recover the true dynamical system is already implemented on Y. So we don't have to use X explicitly. However, of course, data Y depends on the X by its generation.
Well, I think I know, and I think I understand your motivation and intention, but probably me, Jayam, both are wondering about the connections between X and Y.
Yes. So I think let me put my question in a heuristic way. If, to my opinion, your algorithm, your method can give a convergence sequence, convergence something. but we don't know whether the limit is in the limit is a true f. Okay, maybe the limit is something else. You know, so for example, because you had a theory about the restriction on the global attractor, right? You have a theory about A and and then you use invariance. If you restrict everything to the global attractor, then I am fairly sure your result, your approximation is reliable, because the attractor, if I remember correctly, it's almost structurally stable. And this topological property of this spatial set A global attractor will guarantee you your approximation is reliable. But in general, for general F, for general UX, maybe you need to assume something, and maybe this something can be justified by data, like target embedding, because target embedding can help to identify the global attractor, right? And so this is, I mean, yeah. So I am curious about this in general.
Yeah. First of all, I completely agree with your point. So, yeah. So I'm sorry that I will skip the topic related to the question from Tokta-san. But so here, as you mentioned, in order to guarantee the validity of the algorithm, under some error, we require the structural stability of the original dynamical system. However, you have a point of the core idea of my talk. So, as Tokta-san mentioned, so first we have available data which characterize C, the constraint on the realistic realization, and we have the equivalence relation, in this case topological conjugacy. So I am interested in the question what kind of F what kind of F can be that can be realizable under this situation.
I see. Then if this is then I agree with this, because in the end, the F, maybe it's not a true F, but the F you can predict it's the F you want. If this is true, then I am fine with it. Okay, I think it's in general very hard to really get a realistic F. Yeah, so no. Maybe my question is a little bit too picky. So, but yeah, I really appreciate your talk. I like it very much. Amazing. Yes. By the way, can you go to the next slide?
Sure. The next slide.
So there are several direction of research, right? Like 4 direction of research. The last one. The last slide. You conclude with several questions.
In the last slide.
Yeah.
Yes.
I want to make a remark on the last one. So you ask whether like there are other structures. Today you talk about the flow or dynamic system level, right? And you have a topological equivalence relating dynamic system. And in the Lie group theory, this is a Lie group level. So you can also consider the infinitesimal level, which is Lie algebra. So now you can consider vector field. And usually topological conjugacy will relate to some algebraic condition on the, relating the vector field of that generates a dynamic system. So my idea or my remark is the structure on the level of dynamic system should also correspond or should have a counterpart in the level of the tangent space in the vector field. And usually there, you can get some algebraic condition. This is all algebraic structure. This is what I want to say. So if I were you, I want to answer the next question, I will go to the tangent space, go to the infinitesimal level. But of course, maybe your data cannot really give you this structure. I don't know. But as a mathematician, I would do this. Yeah.
Yeah, I really appreciate that kind. I really appreciate that that kind of question in that.
Very nice,
that
very
direction.
nice. Yeah.
Yeah, and
So
also,
the order structure, okay. The order structure on the set of dynamic systems should also give some order structure or monotonicity in some algebraic condition, maybe. Yeah, this is my guess. Yes.
yeah, I really appreciate that. I really appreciate you to pointing out that point. And so actually, the reason why I use dynamical system as a topic here is the mainly three reasons. The first is it is my research topic, and also the second is a topic, and also it is a topic. The topic which is discussed in this NCTS seminar, and the third reason is that as you put several examples, the dynamical systems or the set of dynamical systems allow us to consider the very variety of structures. So in that sense, dynamical system is good example to consider the constraint realization problem in this context. However, I'd like to emphasize again that this framework can be applied for other case, but not dynamical systems. So I'd like to be open to consider the more general case to capture to capture general object which can be realizable within the brain.
Yes. Yeah, exactly. So I think your setting is very general, right? You have a topological space, equivalent relation, subset, and set inclusion. So this is super general. And for example, if besides considering the topological equivalence, maybe you can also consider homotopy equivalence, right? Homotopy equivalence, which is weaker than the topological equivalence. And because for mathematicians, sometimes they want to see whether two objects can be, how to say, are homotopic. And I would be curious how data can really predict this, for example. Yes.
Yeah, I agree.
Very good. Very good. Very good.
Other questions? If not, let's thank our speaker again.
Thank you.
Thanks so much.
Thank you.
Yeah, arigato. Very nice. Yeah.
Thanks so much.
I mean, this is new to me. I never thought of this question, and yeah, very general, very beautiful, nice. Yeah. So can you tell me why Japanese mathematicians can always come out with this novel research?
I don't know.
Yeah. I am actually I'm actually searching that I'm actually searching that person to do latest thing. Yeah.
Good. By the way, because some audience are here, maybe let me introduce. Ding Yang, are you here? Hello, Ding Yang. Chen Qianxiu 老师. Hi. Let me introduce some guy to you. Hey, Ding Yang, say something. Hello.
Hello. Nice to meet you.
Let me introduce Ding Yang to you. He is a mathematician expert in synchronization in water wave, traveling
Sorry, hold on a
wave,
sec.
relation
Hold on a
diffusion
sec.
equation.
Hold
Yes.
on a sec. After I stop
Sorry. Yeah.
yeah.
Now you see everyone, right?
Okay.
Hi.
Thank you so much. Nice to meet you.
Yeah.
Nice to meet you.
Yeah.
Nice to meet you guys. Thank you.
Yes. Yeah, and Ding Yang and Professor Chen Xianxiu, expert in diamond system bifurcations.
Hello.
Yeah. And Xu Haoze, Xu Haoze, right? Hello? Haoze. Okay.
Hello.
Yeah, Haoze
Hello.
is a PhD student in Tohoku University under the supervision of Hayato Chiba.
Oh, yeah.
Yeah. Expert in generalized spectral theory. Equation.
Not expert, please.
You know, Chinese and Taiwanese are always very modest, okay? Yes. Very nice. Yeah. Good.
Have we met each other before? How's this in university?
I guess no. Do you know my supervisor?
Yeah,
Maybe
sure.
can you turn on yours? Turn on your camera
Okay.
so that people can see you.
How?
Maybe from your face. Have you
Hi.
ever met?
Yes, I guess so. So you went to Tokyo University to attend some conference.
Yeah.
If you remember the AIMR. Yeah. No, I remember. Hi.
See? Haoze, you should always turn on the camera. That's how you make friends, okay? Yeah, and Tintin, Davey, hi, yes, Professor Chen. Yes, very good talk, Taiki. Thank you.
Yeah, I thank you very much for again for giving me such great opportunity. Yeah.
Okay, then maybe we close here because it's already 1.5 hours.
Yeah.
Okay.
Yeah.
Yeah. Okay.
Okay.
Thank you for being here. See you next time.
Yeah,
Yeah.
friends, see you next
See
time.
you.
Okay, bye. Have a good day.
Bye bye.
Bye-bye.
See you next time.
Bye.
Bye.